that is not invertible is sometimes called, yes, singular or singular matrix is fine. What's the identity matrix times anything? Anything, yeah. So 1 0 0 1 times 2 5 should be 2 5. So you have 1 0, lay it on top of the 2 5, 1 times 2 plus 0 times 5, that gives you the 2. And then 0 1 on top of the 2 5, 0 times 2 plus 1 times 5 gives you the 5. True or false? A matrix times its inverse is the same thing as the inverse times the matrix equals the identity. True. That's the definition of an inverse. Okay, before we start our lesson on inverse matrices, I'm going to send you back to the group activities from last class. Where you're going to test each statement using the matrices, vectors, and scalars that I've given you, mark them as true or false for this example. And then feel free to use technology after you've done a few by hand, just to get the hang of multiplying and adding and subtracting and matrices. Okay, so A plus B equals B plus A, was that true? Yes, and I chose these carefully to sort of be representative of what always happens, right? So A plus B equals B plus A is true. In general, matrix addition is commutative, right? Because you just add component-wise, doesn't matter which direction you add in. But A times B, does that equal B times A? No, not usually, yeah. In general, that's not a rule. Okay? Oh, yeah. Yeah, you might get a piece of it the same, but yeah, not exactly the same. Okay. I'll look at it later. Okay, how about the distributive property? A times B plus C, does that equal AB plus AC? Yes, that was true. Okay, so the distributive property holds, except then we move on to D. What was this true? No, why? What's the problem here? It's the commutative thing. If you were to distribute that A, it should say BA plus CA because the A is on the right, right? So this one was false, right? And in E, I did it correctly. If I want to do B plus C times A and you distribute that A, it has to go on the right of both of those matrices, right? Because the order of multiplication with matrices really matters. And so this one was okay. How about the associative property? Does it matter where I put the parentheses if it's all multiplication, some scalars? That was false? Right, yeah, I changed the order too, yeah. Yeah, this one was false. Yeah, A, B, and BA were different. But I think in G, nope, I didn't. Okay. Is the identity times A equal to A times the identity both equal to A? Yeah, this is true in general. So that's one instance where you can commute, right? Where multiplication is commutative if you're multiplying by the identity. All right, if A times B equals A times C, if we were dealing with just regular arithmetic, it would have to be the case that B equaled C, right? But in this, with matrices, is not correct, right? Because when you multiply A times B with the matrices I gave you, and then A times C, you get the same thing. You get the same answer. But B and C are not the same matrix. So this is not something you can assume when you're dealing with matrix arithmetic. A times B transposed, is that, can you sort of like distribute the transpose? Was that true? I don't know if anybody got this far. This one's false. multiply A times B and then transpose, switch the rows and the columns. It's not the same thing as A transpose times B transpose. What it is the same as is B transpose times A transpose. So in general, that's the rule for transposing a product. And I encourage you, like if you didn't finish this right now, to go back and do the calculations and just be like, oh, huh, that's cool. Interesting. K, any guesses for K? True? All right, cool. It is true. I find that surprising because, like, if you think about it in terms of matrices, maybe it's not surprising, but if you think of it in terms of standard arithmetic, if that transpose were like an exponent, like you can't usually do that over addition, but with matrices that works. Okay, last one. A times D does equal 0. With the two matrices I gave you, when you multiply A and D together, you do get 0. But is A 0 or D 0? No. So this is another weird thing that doesn't match standard arithmetic, right? If you multiply two matrices together and get the 0 matrix, a matrix full of zeros, A, like either of those two matrices doesn't have to be 0 to make that happen. All right, and number 2 is just an interesting example coming up with a matrix that's not the identity and is not 0 that can commute with A, where A times B equals B times A. But we're going to skip it for now. Okay, so today, lesson 14, we're going to talk about inverse matrices. What is an inverse? How do you find it? And how do you use it to solve a matrix equation? All right, so I want to find the inverse of A, which is 1, 4, 1, 6. I'm going to show you two different ways, and we're going to check that the answer is actually an inverse. So for a 2 by 2 matrix, there's a handy little formula for finding an inverse, right? So if A is A, B, C, D, then A inverse is 1 over AD minus BC times this matrix, the matrix A, but like rearranged a little bit. A and D swap places. B and C stay where they are, but you make them the opposites. So that's the formula from your reading. I do derive the formula for you if you're interested. So let's start by using this formula to find the inverse of 1146. Okay. So I'm going to have 1 over AD by minus BC. What is that quantity called from your reading? Determinant. The determinant. Yeah. AD by minus BC is called the determinant. When that number is 0, you're going to have a 0 in a bottom of a fraction. Can't do that. Then we say there's no inverse. All right, so AD minus BC in this case, so it'd be 1 times 6 minus 1 times 4. And then just rearrange the numbers in A. So the 6 and the 1 swap. The 4 and the 1 stay where they are, but you make them their opposites. And I end up with 1/2 times 3 negative 1 4 1, which is, oops, I did the 1/2 in my, I jumped ahead there. That should be a 6. All right, then I have 3, 2, negative 1/2, 1/2. Yep. There we go. Thank you. All right, so to check that that actually is the inverse, right, so there's my inverse matrix, finished. To check that two matrices are inverses of each other, you multiply them together and see if you get the identity. So let's just verify here. So I'm going to take 1, 1, 4, 6, and multiply by this matrix I just found. No. Technically, if you really want to verify, you should do both orders to show that you get the inverse either way. I typically just do one and I'm satisfied that I did it correctly. All right, so you'd take first row times first column, 1 times 3 plus 4 times negative a half. So you get 3 minus 2, which is 1. And then you do first row times the second column. That would go in the first row, second column of the answer. 1 times negative 2 plus 4 times a half. So that would be negative 2 plus 2 is 0. Second row times the first column. 1 times 3 plus 6 times negative a half is 0. And then first row, second column, I get negative 2 plus 3 is 1. So it is the inverse. All right, so we found the inverse one way using the handy little formula, but it only works for a 2 by 2 matrix, that little formula. So there's another way to find inverses, and I ran out of room here, so I'm going to go to a new page here. You take your matrix, augment it with the identity, and row reduce. Okay. If your matrix has an inverse, you'll end up with the identity on the left and the inverse of the matrix on the right. So I'll have the calculator do this so we can get an idea of how this works. Okay, so I go into my matrix menu, I'm going to edit. I need to put in a 2 by 4 matrix, 2 rows, 4 columns, 1, 4, 1, 0, and then 1, 6, 0, 1, and quit. Matrix, math, RREF, matrix A. And I get the matrix that I came up with using the 2 by 2 formula. 3, negative 2, negative a half, a half. Oops. It's another way of doing it, yeah. When you have a 2 by 2, you don't have to do this. You can use a formula. But if you have a 3 by 3 or a 4 by 4, this is the method you'd have to use because there's no nice little formula for those. And then with the 2 by 2, the way you can tell, with the special formula, the way you can tell if there's no inverse is if the determinant is 0, right? Because you get a 0 in the denominator. If you're using this other method, you can tell that there's no inverse if this doesn't turn into the identity, right? If after you row reduce, you don't get the identity on the left, there's no inverse. The inverse doesn't exist. So you have a non-invertible matrix if you don't get the identity. So that's the other way to find inverses. Okay, once you have an inverse matrix, the reason we like inverse matrices is going to give us another way to solve matrix equations. So far, everything we've done that involves solving a system has been augment and row reduce. Okay, so we actually have another way now. So I'm going to use the inverse we just found, this 3, negative 2, negative half, a half, to solve the equation AX equals B. Okay, so A is the 1, 4, 1, 6. So I'm solving 1, 1, 4, 6. X is a vector because it's bold. and B is the vector 1, 2 that was given. What do the dimensions of that vector x have to be? Yeah, 2 by 1. So think about the dimensions on this guy are 2 by 2. The result is 2 by 1. In order to be able to multiply this matrix times something, the inner dimensions have to match. So it's going to have 2 rows, and the outer dimensions give you the answer. So this has to be 2 by 1. So x1, x2 unknowns. That make sense? Okay. Because sometimes it's unclear, like it's not obvious when you look at this equation how many unknowns you're looking for. So sometimes it's worth writing it all out. All right, so to solve this, instead of augmenting and row reducing, multiply both sides by A inverse. So A inverse is 3, negative 2, negative a half, times 1, 1, 4, 6, times x1, x2. So I multiplied on the left side on the left by A inverse. So keep in mind, matrix multiplication is not commutative. So if you multiply on the left side, you have to multiply on the left on the other side of the equation too. So I'm going to put A inverse here. 3, negative 2, negative a half, times 1, 2. And then what is A inverse times A? What do you get when you multiply in matrix times its inverse? The identity. So this is 1, 0, 0, 1 times x1, x2. And then when you multiply these together, let's see, we're going to have 3 times 1 plus negative 2 times 2. So that would be 3 plus negative 4 is 1. And then negative a half plus 1 is 1/2. And then what's the identity times the vector x1, x2? x1, x2, yeah. So this is the answer. There's your solution. And then if I want to confirm using row reduction, so I'm going to put in the matrix A and augment with 1, 2. So I need a 2 by 3 matrix. 1, 1, 4, 6, and then I'm augmenting with 1, 2. So this is how we would have solved this equation before today. Quit from there. Negative 1.5. So you get x1 is negative 1, x2 is 1/2. So our new method works. Oh, no, it should be negative 1. I messed up. 3 times 1 plus negative 2 times 2. So that should be 3 plus negative 4 is negative 1. Good catch. All right. So we can use this rule, this like multiplying both sides by an inverse matrix, to solve more complicated equations involving matrices. So I'm going to solve this. A, B, and C are all invertible, and they're all n by n, which means I can multiply them together and I can add them together. And they all have inverses, which means that I can multiply both sides by an inverse because I know it exists. So the goal, just like in a standard algebra class, is to get x by itself, trying to solve for x. So let's try to undo this A thing first. So if I multiply both sides by A inverse, on the left, What's A inverse times A? The identity. Yep. And so those just cancel. We don't have to write the identity. It's like writing 1 times something. You don't need to write it. So now I just have B plus CX equals A inverse C. What should I do next, do you think? Trying to get X by itself. Subtract B. Good. So CX is A inverse C minus B. And then how do I undo multiplication by C? Multiply by the inverse of C. And you have to do it on the left because the C inverse has to touch C. Like if C times X times C inverse, you can't rearrange the order. So you have to put the C inverse specifically next to the C. So I'm going to multiply both sides of this equation on the left by C inverse. So C inverse CX equals C inverse times all of this, A inverse C minus B. So the C inverse C, those cancel, they make the identity. So I have X equals C inverse times A inverse C minus B. And we just talked about when we were doing our activities from the last class that the distributive property holds with matrix multiplication. So if you want, it's not really more simplified, but you can distribute that C inverse. You can get C inverse A inverse C minus C inverse B, and either of these would be acceptable. Be careful not to cancel your C inverse and your C here. They're not touching. Matrix multiplication is not commutative, so you can't make them into the identity. Yeah. We were solving for these unknowns, x1 and x2. So this represents a system of equations, right? This says that x1 plus 4x2 equals 1, and x1 plus 6x2 equals 2. Right? Because when you multiply these, x1 plus 4x2 gives you the first entry, and x1 plus 6x2, when you do that multiplication, you get 2. So we were solving for those two unknowns, x1 and x2. So normally we would just set up an augmented matrix and row reduce. This is a new way of doing it. It can just work in the matrix multiplication format without having to translate. All right, back to number 3. This x that we just solved for, is it a matrix? Is it a vector? What's its size? It's a matrix, yep. How big is it? N by n, yeah. Because I told you all of A, B, and Z were all n by n matrices, which means when you multiply any two of them together, you get another n by n. Add and subtract them, you get another n by n. So it's n by n. Okay, so that's it for the demo portion. You can work on the activities.